Wishing you a very happy and prosperous new year. On behalf of CBIP, we extend a hearty welcome and sincere gratitude to the resource speakers, Professor Mahendra Singh, Dr. Sanjay Rana, Dr. D.S. Subramaniam, Shri Vivek Tripathi, Shri V.K. Rastogi, Shri Sudhanshu Nigam, and Shri Naresh Sharma. We also welcome Shri Rajiv Kumar Suklekar, Member Engineering, Narmada Valley Development Authority, Mr. Aditya Kumar Dinkar, Secretary CBIP, Dr. G.B. Patel, Director WR, and other esteemed guests and dignitaries. We convey our sincere thanks to all professionals for their time and presence for 2 days virtual training on the topic on construction of dams in weak rocks. Execution of dams in multi-purpose water resources projects located in complicated geological settings and weak rocks is a challenge to engineers. Such weak rocks have often created problems leading to cost and time overruns. There is a need to know the latest in the field of geological exploration, design, and support system to minimize such problems and also to find appropriate and economic solution for such problems. Both design and construction engineers would always be keen to know what advancements are taking place in their respective fields so as to utilize that knowledge for most economical design and construction of dams in such weak rocks. The objective of the workshop is to provide a forum for discussion and interaction amongst the participants to discuss appropriate measures needed for successful execution of projects in weak rocks. May I now invite Dr. G.V. Patel, Director WR, to welcome Shri Rajiv Kumar Suklekar ji.
Thank you, Kalpana. I welcome all the participants and faculty members. A special welcome to Shri Rajiv Suklekar, Member Engineering, NVDA. Sir, we also thank you for giving us opportunity for this training program and getting associated with the NVDA officers. सर जैसा आपसे डिस्कस हुआ था, कंसीडरिंग द वेरी हाई नॉलेज ऑफ एनवीडीए ऑफिसर्स, इस केस में हमने 7 फैकल्टीज रखी हैं. सर हम इस प्रोग्राम को एक फैकल्टी से भी मैनेज कर सकते थे, लेकिन आपकी इच्छाओं को देखते हुए, एनवीडीए का नॉलेज देखते हुए हमने 7 फैकल्टीज रखी हैं. दोज आर एक्सपर्ट इन देयर वेरियर फील्ड्स. 3 फैकल्टी आ जाएंगी और 4 फैकल्टी सर कल आएंगी. वी होप जो आपकी इच्छा थी इस प्रोग्राम से दैट विल गेट सर, एंड ऑल द पार्टिसिपेंट्स विल बी हाईली बेनिफिटेड with this 2 days program. So again, I thank you for giving the opportunity. Sir, before starting this program, may I request Suklikar Sahab to say a few words about the program. Suklikar Sahab.
Thank you, Mr. Patel. I welcome CBIP officials and dignitaries who are who will be delivering our the specialized knowledge regarding the dam foundation of weak rocks, and my NVDA fellows. This program of construction of dams on weak foundation is very, very useful for our organization at present, because at present we are taking up many major dams, basically on because NVDA's jurisdiction is limited to Narmada River Basin. So at many places there may encounter some rocks, but at many places there is always a possibility that weak foundations, sand foundations, or this type of foundation that may encounter. For coping up with the problems during construction of these dams and barrages, and during the next 2-3 years, we will be definitely enlightened with the knowledge which is being given by the respected dignitaries. So I will always be on the screen listening to the lectures keenly, and I also expect my fellow NVDA officers to listen carefully so that, and if there is any question or any queries regarding these, please don't hesitate to ask the respected dignitaries, because they are the specialized persons who will be only the persons to resolve our problems. Definitely, I again I pay regard to Mr. Patel, who is always having interaction with me with his CBIP other officials. I again welcome you all, and please, I wish you that you go ahead and please complete the lecture, and I will also be there. Best of luck. Thank you very much.
Thank you, sir. Thank you, the leader, sir.
Thank you, sir, for your thoughtful and illuminating opening address. Ladies and gentlemen, now may I invite today's first resource speaker, Professor Mahendra Singh, for the presentation. Let me introduce briefly about the speaker. Professor Mahendra Singh is geotechnical engineer from Department of Civil Engineering in IIT Roorkee. He has more than 37 years of work experience, and his main area of interest are rock mechanics, strength and deformation behavior of jointed rocks and rock masses, stability of soil and rock slopes, landslide analysis and mitigation and tunnels, underground excavation. He is recipient of awards from ISRM, TT and IGS HEICO numbers of times. He has guided many PhD and MTech students in the field rock mechanics and contributed many papers in the national and international journals and in the conference publications. Now I request Professor Mahendra Singh to make the presentation, please. Over to you, sir.
Thank you very much, Honorable Chief Guest and dear friends. So I'm Mahendra Singh here from IIT Roorkee, and let me see if my, can anybody confirm if my screen is visible?
Yes, sir.
Yes, sir, it's visible.
Okay, thank you very much. So again, very warm welcome to this lecture, and thanks to the organizers for giving me this opportunity to be with you. And I'll be talking about the rocks, in fact, because this is a very new discipline, and in many of the engineering colleges or at undergraduate level, people are not aware with this material. So with this brief introduction of the subject, let me start. And the topic on which I am going to talk is characterization of the rocks and also rock masses, and how we can use this characterization in rock engineering. So let us see means what is characterization and why we do the characterization of the rock or rock mass, or maybe you can start with the characterization of other materials like soils. So our objective, in fact, as maybe engineers or maybe geologists, as far as this field is concerned, where you are related to dams, so we want to know the characteristics of this particular material. Characteristics means we want to characterize it. We want to know how much load it can take. We want to know how much deformations it is going to have, and also at the same time, many times or rather, how much permeability this particular material is going to have. Now, as far as the rocks are concerned, it's a very relatively new subject. So we will be focusing more on strength and deformation in the present lecture. So as I told you that we want to know about this material, which we are calling as rock and also rock mass. I'll be differentiating these two terms later on. And it is not a very good understandable material. It was formed under very uncontrolled environment. The geological formations occur under such an environment which is beyond our control. And also it is very complex as far as its engineering response is concerned. Means if you want to know its strength, it's not that easy. If you want to know how much settlement it is going to offer, it is going to create, it is going to be there, so that's not easy. And it's not easy to understand this particular material. And above all, it's not also feasible at many a times, or it's not easy to test this material. So we have to derive the properties, we have to assess the response, we have to get it indirectly many a times. And then, as I told you, that the objective is that we are going to use this material in design. So in general, this material will be available at many slopes, in tunnels, foundations, and specifically here, you are very specific here. So dam foundations, many a times you will be having rocks. These rocks will be fractured, they will be jointed. There may be some other material also, as was being told, and but I'm concentrating on the rocks. I take back, yeah, I take you back to around maybe 60 years back when this particular discipline started, and what was one of the most important event which was responsible for starting this particular discipline of rock mechanics was failure of one very famous dam. This is a very famous event in the history of rock mechanics, when there was a dam called as Malpasset Dam in France, and in 1959 it failed. So that was the one of these events which triggered, which started, which forced the people to think how to go ahead with what were the reasons, and how much important the engineering geology is. So that was the time when it was realized, and people started working on rock mechanics. So this was probably one of the event which gave a direction to the thinking towards this rock mechanics discipline. And as we know today that these engineering geology, the geological features are extremely important for a structure like dam. And a lot of analysis was there, lot of discussions were there, and finally it was observed that geological discontinuities like fractures, bedding planes, foliations, they play a very, very important role, and we have to bring them in the analysis. This is another example which again around the same time, 1963, there was a failure there was a big slide in Italy. This is called as Vajont slide, and that also was an important event when we started, or the engineers started thinking about this geological features, how these geological features they govern the stability of the structures. So with this brief introduction, I'll just explain now how we go ahead with the characterization. So as I told you, rock mechanics is a relatively new discipline. And after these events, the International Society of Rock Mechanics was formed in 1962. And first International Congress was in 1966. And then every 4 years, there are international congresses. And then the discipline is then developing very fast. In nutshell, this branch is the mechanics. This rock mechanics is defined as the theoretical and applied science of mechanical behavior of rocks. It can be applied to any field, to civil engineering, to transportation, underground powerhouses, etc., etc. And role of discontinuities is very, very important in this particular discipline. So coming back to our own country, there are a lot of developmental activities which are going on, and many of you people are associated with these activities. And everywhere, and it might have been, you might have seen that most of the times At many places you get rock, and that rock which you get is not a very strong, a very intact or massive rock. Rather, it is fractured, and you can see in the photographs, it is foliated. There are blocky masses. There is disintegration of rocks, and this is the thing which we have to take into account. So these features will be very, very important. Again, few more photographs I'm showing here to emphasize the importance of these geological features, which make this discipline different. You can see here on the top left side, there is a bridge, and it is almost 50-meter high bridge, and you can see the fracture planes here. The middle photograph, I have shown you the foundation of this bridge, and there is a boat here, and you can see a person in the boat, and you can see the size of the blocks. So in fact, this rock is not an intact rock. We will be calling it as rock mass. Rock mass means there are number of blocks, and it's a pile of blocks. It is an assemblage of blocks, and these blocks are separated by these features, geological features. And these features, the structural features, the planar features, they are dipping in some direction. They will be having some dip. There will be some dip direction. And also they will be having their own characteristics in the sense that they may be rough, they may be smooth. You can see in the right top here, you can see these fractures, and these fractures are very smooth. You can go and touch them, and you can have the feel of the roughness of these features. And also you can assess whether they are massive or they are likely to fail. So in nutshell, the rock mass will be anisotropic. It will be having a complicated behavior. Say, for example, here on this side, you can see this is again a blocky mass, but there is a lot of cementation in the joints. So these particular features we have to consider. We have to think of the dip directions, the roughnesses, and all that. So now coming to, as the topic is the characterization. And main objective of the characterization is we want to know the properties. As civil engineers or as engineering geologists, I will be interested in finding out how much is its strength and deformability. Permeability aspect I am not touching at the moment. And when we talk about the rock, so we have to start with the substance, the intact rock. Though in the field you will not be using these properties directly, but we have to start with the basic unit, basic fundamental. So, and then this is going to form what is called as jointed rock or rock mass. So we will be then proceeding further to get the properties or characterization of the rock mass. So as I have been telling you that in the field, the rock mass tests are extremely difficult, though for a dam, it's a big project. You can do the test, but it is very costly. Before doing the test, we should be able to derive some properties. So I'm writing a statement here that shear strength parameters are derived. They are not obtained. So most of the times we are not able to test it. Rather, we are going to guess it. And how we guess it? We start with the intact rock pieces, and then we get information about these discontinuities. These discontinuities are nothing but defects, and how much defect, how much incompetency that particular feature brings, that from there we are going to derive the parameters of the jointed rock. So let us start with the intact rock, and many of the things are known to you. So we start with getting the intact rock specimen. Intact rock means if I go back to this any of these photographs, then this material which you can see here, the material which is free from defect. If you take a small core, if you take a small block, and then you can drill it in the lab, so that particular material is intact. So here you can see the course here. So we start with the drilling operations. So you do the drilling in the field using drilling bits, and then you get these cores. I'm not going in detail, so I just want to give you some idea. So we get these cores, or sometimes we bring the chunks also, and then drill it in the in the laboratory. And after drilling it, then you do the cutting and polishing, and then you prepare the specimen. So initially we have to start with that fundamental unit, that is the intact rock. And you will appreciate that we have already done a lot of work. You might have done a lot of work with soil specimens. Soil is not a ductile material. Uh, rock is a, sorry, soil is not a brittle material. When it fails, it does not fail in a brittle manner. It does not fail violently. Energy is not released so violently as it is in case of the rocks. So when we do the testing for the rock specimens, we have to be much more careful because it is a very brittle material. You can think of glass. If you are working with glass, glass is highly brittle. Rock is not that brittle, but when you are working with the rock specimens, we have to be cautious in the sense that during cutting, during polishing, during transportation, there is no crack which we initiate, because in brittle material, generally crack can be developed very easily. So strict requirements are there as compared to soil specimens. In soils, you have done the test. So similar kinds of the tests are done here. Little bit difference is there. So we are going to get the properties of the intact material. So that is our first step in the direction of the characterization. And there are a number of tests which are performed. Say, for example, uniaxial compression test, just like in soil. Then point load strength. I'll discuss it in brief. Brazilian test, then Schmidt hammer test, triaxial strength test. So there are tests which are performed to get engineering properties, and also there are tests which you perform to get the physical properties. Say, for example, what is the density or the unit weight, or how much voids are there, or how much moisture it can absorb, what is its slave durability index, etc., etc. So just a brief description about these tests. So I start with the uniaxial compression test. So these are the cores which have been prepared for UCS test. You have, as I told you, you have to be very strict as far as the requirement of the specimens are concerned. We are going to test them by applying load in the axial direction. So these bases, they should be perfectly smooth, number one. Number two, they should be perfectly perpendicular to the axial direction. And also the sides here, the sides also should be smooth. Otherwise, what is going to happen is when you apply the load, premature failure can occur, and we will be underestimating the strength values. And then the testing procedure is similar to what you do in case of soils. So here I have shown the picture of the triaxial testing machine. So you can do triaxial test as well as uniaxial test here. Uniaxial means we are not applying any confining pressure. So you are going to put the specimen here, and then you are going to apply the load. You are going to measure the axial deformation, and you are going to measure the load, and then from there you can get stress strain plots. You can also glue these strain gauges, and you can find out how much is the lateral expansion in this specimen, and then you can also plot the lateral strain. So once it is loaded, it fails. So this is going to fail in a brittle manner. The degree of brittleness will depend on the type of the rock. For shales, it may not be so brittle. For granite, it will be a very violent failure. And generally, after the failure, we must observe what kind of the failure was there, whether it was brittle, it was ductile, or there was clear-cut shear plane like this, or there was vertical splitting like this. So these kinds of the informations we are going to note down, and these types of the information give us idea what kind of the material we are dealing with. So the failure modes at the end of the test may be splitting, it may be shearing like this, and there may be dead end formation, but sometimes you will find that this portion remains intact. So it happens when it is a kind of ductile material, or there can be bulging also. So if it is a shale kind of the material, then like soil specimens, it can bulge. There may not be a very clear-cut failure. Then we plot this stress strain curve. Here you can see on the x-axis, this is the axial strain, and transverse strain, the diametral strain also we have plotted, and the curve goes like this. This curve gives us very good information about this particular material. And from here, if I take the peak stress where the failure occurs, this value we are going to call as the uniaxial compressive strength, UCS. Means without any confinement, the rock, it is intact rock. Please note, it is not the jointed rock. It is not the rock which actually bears the load in the field. So it is a small element of that particular rock mass. So this stress is the UCS, and the gradient of this particular curve give you some more information. Say, for example, we can get the initial modulus, we can get the tangent modulus, and also we get the second modulus. I hope you remember these things. Modulus means it gives us the idea about the deformability of this particular material. If it is a highly deformable material, then failure strain will be high and the modulus values will be low. If it is the modulus value is high, then it is going to have a smaller failure strain. Generally, we are going to calculate this term, which is called as modulus ratio. And this modulus ratio is nothing but the ratio of the modulus and the UCS. And it is a measure of inverse of elastic strain. So if you reverse it, you get idea about the strain in the material. So we get from this graph, you get UCS and you get the modulus values. Now these two values are important in characterizing the rock. One thing is we are talking about the strength. Second thing is we are talking about the modulus. So we are having the idea whether it is a very strong rock, number one, it is having very high strength, low strength, or something like that. And also we have the idea whether the likely strain, likely deformation is going to be large or it is going to be very small. So there are these two informations are very important informations which we get from this particular test. So when we do the classification, now there is a term which I have used, characterization, and here I am using the term classification. So classification means you have number of objects and we divide those objects into certain classes, and every class will be having certain common attributes. Say, for example, if I talk in terms of the strength, so very high strength, these are the categories in which you can divide them. This is Dear-Miller classification, which was proposed in 1996. And here in Indian scenario also, there is a lot of work which has been done by Professor Ramurthy at IIT Delhi and other researchers. So this kind of the classification system can be used. So it gives us the idea. If I say, let us say the rock is having moderate strength or high strength or very high strength, then there are certain numbers which are associated with these terms. So we can have the idea, okay, it is going to fall in this range. High strength means 100 to 250 MPa. Low strength means 5 to 25 MPa. Medium strength means 25 to 50 MPa. So many of our rocks will be in our Himalayan region will be somewhere here. And so we get the idea about the strength, and also Using this modular ratio, which I defined here, modulus ratio ET50 upon sigma Ci, this gives us idea about the deformability. So if this modulus ratio is high, let us say it is 500, more than 500, that means the deformability is small. It is a very competent kind of the material. Then we are likely to have low strength. So high modulus ratio means it is very competent. It is going to give you very small deformation. If the modulus ratio is low, then it is going to give you higher strain, means the higher deformations, and modulus this ratio is low, and medium is this range. So depending on the experience, depending on the field conditions, people have come out with this classification, which initially started with Dear Miller. And so one can classify the rock by these two categories. So say, for example, we will be using two-lettered symbol. Say, for example, DM. D stands for, it tells you the category of the strength, and M tells you the category of the modulus ratio. So D here is strength. So strength means medium strength. And M means, M is here, so medium modulus ratio. So if I go as per Dear Miller, then D is low strength. So low strength, it is 18.1 to 28.1 to 5 to 56 MPa. So in this range, the strength is lying, and the modulus is lying in this range. So these two letters give us idea about the strength as well as deformability. One very good point about this classification, Dear Miller classification chart, is that you can plot these the values of the modulus and strength here. So on x-axis you have the strength, on y-axis you have the modulus, and it has been found that a particular type of the rock lies in a particular region. Say, for example, here if you look at this one, so one is quartzite. So maximum number of data taken from worldwide literature were found to be lying somewhere here. Similarly, you can see number 2 is gneiss. So in gneissic rocks somewhere here. So in fact, this gives us a very good idea. Even if I do not have any information, I know only the geological name of this particular rock, I can have the idea, okay, the strength is likely to vary from here to here, and the modulus is likely to vary from here to here. Or if you are able to do some tests, let us say you have done the UCS test and you put the value here, and then from there you can have rough estimate about how much is going to be its modulus. So this classification system or this characterization is very handy. It is very useful when you start working with the material, when you don't have much data, you have only maybe name, or maybe you have done some indirect test to get the UCS only. So once from the UCS, you can some judgment you can make about the deformation also using this available data. So here again on this chart, again these regions I have shown, not me. This is from the literature. So for different rocks where they lie in this particular region, so you can make use of this classification system. Now there are a number of other classification systems available because it's more or less, I should say, arbitrary, though it is based on experience, but we fix up the values. Very high is from here to here, high is from here to here. Maybe some other person, or maybe people working in different countries, they will be having some different perceptions. So ISRM has come out with this strength classification where they have divided into different categories, right from less than 1 MPa to more than 250 MPa, and one can use these classification systems also. And here I have given you the typical values of the properties of different kinds of the rocks, so one can get the idea where as per the project requirement. Now, I have discussed here the UCS, which is though it is very easy, but again, it's not feasible many a times, especially at the very initial stage. It is not possible to do the drilling. Drilling is again a costly affair. So we can get idea about the strength from some indirect methods also. So if you are working at a very DPR stage, at a very preliminary stage, we can use these indirect methods, though it is recommended that we should not use them for design, but for initial assessment, we can use these methods. So one such method to get the UCS is point load strength index. And the test is very simple. What is there? You can see here there are two cones. So there is a standard dimension of this cone, and there is a standard material also. Its hardness is standardized. And between these two cones, then you put a specimen. This specimen may be regular, it may be irregular also, it may be a core, a piece of core also if it is available. And then we apply the load. So here is a jack, you can see, here is the jack, and this cone will lift up, and then we apply the load, and the failure load is obtained. So from the failure load, then we can have roughly the idea about the strength. In this particular lecture, I don't think I should go in much detail because I have to cover a lot. So I'm just giving you the idea that once you get the load, and then from that load and from the dimensions of this piece which you are testing, you can find out roughly what is the point load strength index. We call it point load strength index, and from there we can get its UCS. And when you test it, there are certain requirements that the failure should occur like this only. If it is only chipping a small, it is taking out a small chip, we should not consider this test, and we should neglect this test. Or if there is a cores are available, then also you can do the point load strength index test. For UCS, you should have at least a length of the core should be more than 2 times the diameter or equal to 2 times the diameter. If that is not available, then you can do this point load test. And here again, it is shown which tests are valid and which test is not valid. So normally we do large number of tests, maybe at least 15 to 20 these point load strength index test, and then you will be getting very high scatter also. Then we remove the outliers, and then you get the average value of the strength. If it is irregular specimen, then also you can test it. And there are requirements which are available in the literature. I'm not going into those details. So you can get the UCS, you can get the point load strength index. And then from that point load strength index, this is the point load strength index, load divided by this dimension. And this dimension has, it may be around 50 to 30 mm. So if it is exactly the standard size is 50 mm, if it is not 50, because it's not possible to have always 50 mm, so then a correction is applied, and based on that correction, you get this point load strength index. And this point load strength index is multiplied by a factor which depends on the type of the rocks. So it is around 20 to 25 times IS50. We take sigma CI. Sigma CI is the UCS. So we can get the UCS by conducting point load strength index test. Point is, these are rough values and not recommended for design. Then you can also get the idea about the strength using Schmidt hammer test. It's a non-destructive test. Many of you might have used it, especially for concrete. This test gives you the property of this surface. So there is a spring inside it, and then we find out how much is the rebound value. So the rebound depends on the properties of this surface. So if the rebound is higher, the strength is higher. If the rebound is low, the strength is low. So the charts are available for the Schmidt hammers, and they give you some rough value of the strength of the rock, but please note that we are going to get the property of the material which is at the surface. So maybe at the inner side this may be different, here it may be different. So if the rock is weathered, you are going to get the properties of the weathered rock at the surface, not the intact material. And many times it may be advantageous also, because you may be interested in getting the properties of the surface rock only. Another test which we normally do with rock is tensile strength. You all have done soil mechanics courses, and you must be remembering that soil do not have tensile strength, but rock does have some tensile strength, and we can take advantage of this particular properties, especially where the tensile stresses are going to develop. So for intact rock, the tensile strength can be obtained by this indirect test. Again, this is an indirect test. So you can see here there is a rock specimen which is kept here. There is standard dimensions of these jaws, and then a load is applied, and this particular specimen should crack. The crack should initiate from the center. So what is going to happen when you apply load? Here there is some standard area which is in contact with the steel platen, steel jaws, and when the load is applied, there will be tensile stress which is going to develop here in this direction. So what's going to happen is that tension is going to develop here, and it's going to fail. So we have to observe it very carefully, that tension starts developing at the center. If it is not developing at the center, if it is chipping here, then we have to discard this test. And then equations are available using which one can find out the tensile strength. Then there are indirect tests like wave velocity tests. These you might have been doing. So this is the rock specimen. These are the transducers. We apply the P waves or S waves, and then using those we get the wave velocity, and that wave velocity is correlated with the properties of the intact rock. Then slate durability test. So here it is, there are two drums here, and these are two small reservoirs. So you can fill it with water or maybe some other fluid which is there in the atmosphere there. And then rock pieces are kept inside this drum, and it is rotated. And then we find out how much is the effect of the cycles of drying and wetting when it is when the rock is subjected to those cycles of the wetting and drying in that particular fluid, generally water. So there will be some rocks which will be disintegrating. So you give number of cycles, and after that you dry it, you find out the weight, you find out the dry weight, and then from there you get the idea whether it is susceptible, whether the cycles of wetting and drying are going to have some detrimental effect on the rock or not. So these are the simple tests. Now next test is the traction strength test, so which is philosophically same as soils. So what we do here, there is a specimen, rock specimen, and this rock specimen is subjected to confining pressure from all the sides, and then we apply load in vertical direction, and from there you get the traction strength. In the field, the material is always under some traction condition. If you are having the rock foundation, the dam foundation, so below the foundation, the rock will be having some material around it. So there is some confinement. There is always some confinement, which is there, which is trying to support it, which is trying to make it not to fail. So it is supporting it from the sides, and when there is support from the side, the load bearing capacity of the material increases. So idea about this traction testing is, if there is some support, if there is some confining pressure, how much is the increase in the strength of the material? So those expressions, those equations, those correlations they are called as strength criteria. So we try to get them using the triaxial test. So what we do is, here is the triaxial testing machine, and here we have already kept one specimen inside this cell, and then there is a fluid, generally mobile oil here, and we apply the pressure and then apply the load, and then at different confining pressures we do the test. We get the strength at different confining pressures, and then you can plot the Moore circles, and then you can get those C5 parameters, and I hope these terms are not new to you. Then we can get the relationship, how the strength increases, how shear strength increases with normal stress, or how the major principal stress at failure increases with confining pressure, that we get from these tests. So this is the still we are working on the intact rock. So what happens is that it has been found that in case of rocks, the behavior has been found to be nonlinear. So rather than a straight line, there are curved envelopes, and then equations are available. And due to paucity of time, I will not be going in much detail. So in the literature, these equations are available. You can fit those equations, and depending on the particular confining pressure which is applicable in the field below the dam foundation, you can assess the strength. So these are called as nonlinear strength criteria. Lot of work has been done on this aspect in India as well. So here, this is very well-known equation, which is called as Hooke-Brown equation, to get the nonlinear strength of the rock. If you don't have much data, so those parameters of this criterion you can get from the literature, and still we can have some idea about the confined strength. For Indian rocks, for Indian conditions, a lot of work has been done at Delhi, and we at Roorkee also we have done a lot of work, and there are some equations which are available to get the behavior, to get the influence of confinement on the strength of the rock. So say, for example, this equation I am presenting here, I am not going in detail. This was developed at IIT Delhi, and here at Roorkee also we have done a lot of work on these issues. So if anybody is interested, we can go in detail. So let us say we have covered our first thing, that is, we have started with the element, and now we go to the jointed rock. In fact, in the field, it's not the intact rock, it's not this particular material which I am interested in. I am interested in the overall behavior of this entire mass. I am interested in overall behavior of this entire mass. So jointed rocks means not only the intact rock, but the effect of joints. So how to characterize that effect? And it's very difficult. It's in the sense that the failure can take place here. The failure can take place, you can see in this figure, the failure took place along these planar discontinuities. Here, if this tunnel is going to fail, maybe the sliding is going to occur here on this side. On this side, there may not be failure, or if the failure occurs, it is going to be across these joint planes. So failure mode is quite complex in case of jointed rocks. So there are many issues, and it's very difficult to assess this strength of jointed rock. And moreover, nonlinearity is there, and direct shear tests means if we want to actually test this entire mass, if we want to do the entire particular test on this particular mass, the arrangement which we'll have to make will be very, very large, very, very expensive. So and maybe sometimes it's not feasible. So we derive the strength rather than we get it. So I will just cover a few things here. So let us be clear about these terms. One is intact rock. Intact rock means this piece, which I can test in the lab. And I can also test this joint also. I can find out how much rough it is. So This is called as discontinuity. Discontinuity is a general term. So any defect in the rock is a discontinuity. Say, for example, when we drilled it, so there was one joint plane going like this. There was one joint plane was going like this. Another joint plane was going like this. So these are the discontinuities. So we start with the intact rock property. Then we consider the effect of discontinuity, and then we get what is called as jointed rock or end rock mass. Here also I would like to make you clear little bit about the jointed rock and rock mass. When I say rock mass is this particular mass which is an assemblage of blocks of intact rocks. And when I say jointed rock, it's a common term. Even this particular piece, if I take it out, I am going to call it jointed rock. It is not a rock mass. So jointed rock means any rock which has a joint or fracture. It may be a mass or not. So we are interested in mass strength. So based on this discussion, now there can be two major categories of the failure modes which can occur in the field, and I have shown you here that one is the sliding is occurring on the discontinuity. So if that is occurring along the discontinuity, we are going to use discontinuity shear strength. And second category is rock mass shear strength, where the failure occurs along this entire rock mass. So here it is not failing along one particular plane, but it is failing along the entire rock mass. So starting with the first one, so discontinuity shear strength means an example here, you can see the block was there and it slided. So we should know the C and phi of this particular joint plane. And these are other examples of the joint planes. And here it is the rock mass. This was entire rock mass. There were so many blocks. Then the degradation started. There were deformations. And finally, it failed like this. And I have shown you here one photograph of the rock mass failure. So here the failure mechanism is different. So we should decide this mechanism before when you start working or when you are working for a project, what exactly is likely to occur there. So we have to get the shear strength parameters, and we have to characterize the rock in that particular way. So if I start with the first category where the shearing is occurring along the discontinuity, so I'm calling it discontinuity shear strength. So this is a model which shows how the surface roughness of the discontinuities are going to play a role. And then you get the equation something like this: tau is equal to C plus sigma and tan phi, which you already know. So tan phi is the friction angle, phi is the friction angle, C is the cohesion between the joint planes. We can do these tests in the lab along the joint plane or in the field. This is a field shear box which is shown here, and one can get the properties, and one can then fit straight line, or if it is not a straight line, we can fit a curve also, and we can get this equation. And depending on the load in the field, suppose normal stress is here, I can get the shear strength from this curve. And there are simple models available. The most popular model is Barton model, which you can get, you can develop it, you can get the strength from this model. In the field, you have to see these parameters. One is GRC, JCS, and phi R. So you can have you can compare the roughness in the field with these standard charts, and depending on that, you can assign this GRC value. JCS value you can get, it is the UCS of the wall, so you can get it from Squeak hammer test. And phi R is a standard value for given rock. So it's the only thing which you have to get from the field is how much is the roughness. So you can go to the field, you can feel the roughness, and you can assign it, and then depending on that you can develop that equation. So from there you get the strength of the joint. If the failure is through the entire blocky mass, then we have to use some other kind of the equation. So there is one equation which is called as linear Mohr-Coulomb failure criterion, which you already know. It is in terms of C and phi. So we will be getting C and phi of this rock mass. How to get the C and phi of this rock mass? Again, here it is a very, very difficult and challenging task. And most of the times you are going to encounter the problems where you need to know this. So we cannot do field testing, or if it is possible by spending money, if it is feasible and it is justified, one can do it, but many times it's not possible. So we use the classification techniques. So characterization we are doing through classification. In classification, as I told you, we are going to divide the rocks, different rocks, into different categories. So we are going to use classification techniques. And I will give you idea about only two or three classification techniques which are very popular. So the basic classification was done by Terzaghi. It was way back in 1942. And he divided the rocks into these categories. Entire rock mass you have to visualize, then you have to see whether it is hard, whether it is stratified, it is massive, moderately jointed, it is moderately blocky and seamy. So he divided them into these categories: very blocky, completely crushed, and then squeezing, and then swelling. So this particular classification system I have just mentioned here because it is the mother of all other classification systems. The modern classification systems are, yeah, just one point. Based on these categories, then in fact, Terzaghi used it to design the tunnel support here, and how much load is coming on the tunnel, one can find out from this, he has given a table. I'll come to the modern systems. So in that, the first thing is we have to get the what is called as RQD. Probably this is the most common term which you might have heard about. So RQD is the modified core recovery. We do the drilling, and then we take, let us say, 100 centimeter of drilling we have done, and then we consider only those cores which are more than 10 centimeter long. So this 10 centimeter was taken arbitrarily, and then we sum up this core length, and their percentage is called as RQD, rock quality designation, or it is also called as modified core recovery. So this gives us very good idea about the extent of fracturing in the rock mass. This particular term is used now in other classification systems. So first classification system is RMR. So here there are certain parameters. Say for example, uniaxial compressive strength of the rock material. We have already discussed it. So this is also going to contribute towards the overall strength. Then RQD gives you the idea about the extent of fracturing. I was telling you that we start with the element, we start with the properties of the substance, and then we are going to reduce these properties depending on how much defects are there. So rock quality designation gives you how much are the defects. Then again, how much is the spacing of these discontinuities? This is another parameter which this particular system considers. Then what are the conditions? Conditions means whether they are rough, whether they are smooth. If they are rough, then they are going to offer higher resistance. If they are smooth, they are going to offer lower resistance. So these parameters are considered. Then groundwater, whether it is the water is flowing through it or whether it is dry. Based on these things, then the RMR is decided, and then depending on the orientation of the joints, some penalty is decided. Say for example, if it is a horizontal joint and you are applying load in vertical direction, its behavior will be entirely different. But if the joint is inclined and you are applying the load, then its behavior is going to be different. So there are tables available. One can decide the ratings depending on the strength, RQD, condition, and then find out the RMR values. And then based on those RMR values, and then you have to apply the penalty for the orientations, and then you can finally suggest the parameters of the rock mass. So you can see here, they have, this is the weightages, 15%, 20%, 20, 30, 15. These are the weightages to different components. And then C5 values can be obtained. So ultimate aim is we want to get C5, we want to get E, the modulus. These are our main ultimate value, ultimate aims. Then for Indian conditions, a lot of work was done here at University of Roorkee that time, and depending on RMR, you can get C5 values for different conditions. These charts are available, and also you can decide whether if you are working for a tunnel project, whether you have to provide support or not. Now, there is another classification system for the rock masses that is called as Q system, and it uses these parameters, RQD. Again, it gives you the fracturing, number of joint sets, how many joint sets are available there, what is the joint roughness, how much is the alteration. I was talking about there may be weathering of the joint surfaces, so how much weathering is there, how much joint alteration is there, and then how much water is present, and then stress reduction factor, what is the stresses there in the field. So based on this, you can you can calculate this Q value. So in fact, the geologists, you do it very routinely, and based on that Q value, then you can do a lot of things. You can use this chart to decide whether what kind of the support system you have to provide, if it is a tunnel, and also you can come out with the parameters like what is the C value, what is the phi value for that particular rock mass. Finally, I come to now, I was telling you that nonlinearity is also an issue in the rocks. So here is one system which has been developed very recently. It is called as geological strength index. You can go to the field and you can find out whether the rock mass in the field is in which category. You can see here it starts with intact or massive, then blocky, then there is much more deterioration, very blocky and semi, then disintegrated and laminated. So the quality of the rock is going down in this direction. And here you can see in this axis, there is a surface quality, means the surface condition, the joint roughnesses are very, very important. So very good, very rough, fair, smooth, and something like this. And based on these, then you can decide a small range. Okay, my project is somewhere here. So if my project site is somewhere here, I can decide, okay, this value is around 30, 20. So it varies around from 30 to 40. Once those 30 to 40 values are available, then you can use these equations and you can fit. It is something like doing a traxial test in the laboratory. So these equations can be used to get the traxial strength. Here you can see the parameters are there. GSI is there. MJ, MI I have already shown you. The tables are available. You have to do some tests on the intact rock, few traxial tests, and then you can come out with the parameters for the jointed rock. So that is about the GSI. Now for Indian conditions, a lot of work again has been done at Delhi, and these literatures are available at IIT Roorkee. Also, we have done a lot of work, so I'm not going in detail. Finally, this one small thing I'm telling you here, that many a times you will be needing the strength of the rock mass in the field. So this is another classification system. You can say joint factor. Here they consider joint frequency, joint inclination, and also roughness. And based on that, you can calculate this index, and then you can find out the rock mass strength, and then you can use the equations to get the confined strength. If you have RQD, RMR, and Q values, there are some empirical equations available to get these rock mass strength, sigma Cj, and these equations can be used. The idea is that if you have these RMR values, if you have characterization, you have done the characterization of the rock mass, you have the RMR value, you have the Q values, then there are a number of equations available. There are a number of lot of literature is available. You can work out those values of the strength, and from those values you get a range, then you can use your own judgment and you can come out with the design parameters. There is one approach which we have suggested, that we have suggested that you should do some tests. Deformability tests are easy to perform in the field. So you can do a kind of the plate load test and you can get the deformability in the field. And that deformability also can be correlated with the strength using these equations which I have shown here. So one can do all these tests. So finally, I would like to conclude that the assessment of engineering response of rock masses is very, very important when we are going to design any structure. Maybe it is a dam foundation, you are working with dam foundations, or you are working with the slope stability problem there, or you are working with the tunnel. So you have to have the shear strength parameters. And to achieve that goal, we do the characterization. So characterization means we find out the character of the rock, means in the sense that its characteristics, its shear strength parameters. And for characterizing the rock mass, we start with the intact rock. So intact rock properties have to be there. You have to get them. So you can get them done in the laboratory. And those properties, they are going to represent the upper bound values. And in the field, the failure modes are very complex. So in general, these are only two broad categories I'm telling you. Otherwise, it's a very, very complex thing, very difficult to decide. So it is failing along one joint plane. There may or may not be one single joint plane, or it is through the entire mass. So consequently, we have to make a very judicious choice of the shear strength criterion. So, and we have to remember that the shear strength behavior is highly nonlinear, and appropriate shear strength criterion can be used. And in all these strength criteria, you are going to use the rock mass strength, which is a starting point. And it is strongly recommended that some field testing should be incorporated, because we cannot do entire field testing. And also we should not completely ignore the field testing. My personal idea is at least some deformability tests should be done at the site. Once you do the deformability test, that deformability is directly connected with the strength of the rock mass. So we can come out with these strength parameters also of the rock mass. So with this, I think I am able to cover it. It is a wide subject, a wide area, which I have tried to cover within few slides. So I'll be happy if there are some questions or some queries.
Thank you, sir. Thank you for making an excellent detailed presentation on characterization of rock and rock masses and its use in rock. May I request to the participants, if they have any questions, they may ask.
Sir, will it be possible for you, sir, to please provide us these useful notes?
I have shared the PDF with the CBIP.
PDF either
Yes,
soft
sure.
copy.
We will be going to share the content along with the participation certificate to all the individual participants.
Thanks. Thank you, madam.
If any additional material is required, I'll always be happy. Yes, please.
लिख करके दिया था लिख कर तो दे दिया अब ये तो कुछ लोग पूछते भी है
Yes, sir, please ask.
माइक जैसे बटन होगा
कौन सा ये किसके कारण डिवाइस है बता नहीं
Do you want to ask any questions? Mr. Baladara, please.
इस पे
Hello.
Yes, please.
Can I speak?
Yes, please.
Good afternoon, sir. I am Sarabjit Bakshi from Central Border Commission.
Nice to see you.
So it was very nice to have gone through your lecture. It was very educative. Now I have some practical thing if you can help me out, sir.
Yes.
One, I have observed that normally at sites, when we define the stripping limit and when we actually go to the site, I mean, they don't match it. I mean, a lot of stripping has to be done more than what we had envisaged. So how can we be more accurate in that?
What I can understand it's a means a problem of investigations, means we have not fully investigated, and it's not especially in rock mechanics problem and the kind of the geology which we have in our country. It will never be possible to have 100% investigation done and get the full information. So it's only again judgment. We have to judge up to where you are going to get the desired uh, uh, mm, properties. So I think if you include experienced geologists, they have very good, from their experience, they can very easily and they tell you very confidently also, and their judgment is very good. They can tell you up to here you are likely to get this kind of the material. They go all around the area, they look at the exposures, wherever the exposures are available, and from there they have their own tools also, so they can tell you that this is the probable depth up to which you are going to get this particular kind of the material. But it's in our country, the geology is so fragile and so changing that it's very difficult to get the things beforehand. That's why I'm saying that we have to derive the things. So those contingency plans have to be made, and a better solution means best answer has to be given by you people who are working
That
in
is
that.
what we have seen, because when we actually go into the site,
Yeah.
I mean, the investigations are not adequate enough what are being suggested during the DPI preparation. Maybe
Yeah.
that is a handicap also, but I
Yes,
thought.
but it's a practical problem. Even if you do all the investigations, then also you are going to get so many
Issues.
changes. So
So
it's yeah.
second point was that when we, I mean, excavate the banks, I mean, where the dam has to be abutted. So at times we find jointed rock mass is always there. So can we have some idea? I don't know what features we should look at, that how deep is that joint is going to travel. I mean, any rough idea by looking at the features, if I can estimate that this gap which I'm seeing is 2 meters deep, or maybe it is 5 meters deep. I mean, is there any criteria on this thing? Because only one
Yeah,
side is exposed. I
that's
don't have the
I was
3D view.
yeah. So see, the joints generally will have a regular pattern, means the formation of the joints occurs because of certain systematic forces. And if the joint mapping is done, then using the joint mapping, and then they have the idea, okay, there are, let us say, 3 sets of joints, and
Hello.
this particular set of joint is going to have this much mean spacing, this is the likely spacing, and even this is the likely persistence, means from the exposures they can assess it. I do not know if there is some technique available which can work like underground, like they do in resistivity and all that. I am not aware of those techniques. The technology is working, developing very fast. But from the exposures, the geologists do it. They give you some idea. Uh,
I think, sir, we are not able to at times the depth part too. I mean, this sort and this sort we can
yeah.
get it, but the depth into the hill mass, that is a little difficult, because geologists also at times get stuck, because after this all stripping carried out,
Yeah.
there is a problem. I was thinking if with the opening of the joint set or something, if we can have a rough estimate, because that helps me in installing the rock bolts and all. But at times I find it was very difficult to assess whether how deep this joint is going to travel.
But they give you some idea about the persistence, means whether it is a continuous kind of the joint or it is not continuous, and so this kind of the idea they can give you, but exactly getting is uh, not so easy. And as I told you, there may be some techniques uh,
No,
where
that resistivity, what you are telling, sir, is not possible every time, because when we are benching down, we have to bench around 60 to 70 meters. So
Mhm.
at any elevation, at 1 or 2 elevation, you can do it if required. Because when the works is in progress, mobilizing all this resistivity equipment and calling the contractors, doing studies, getting the results after 10, 15 days, you cannot stop the works. So
Yeah.
point is, we have to take a decision at the site
Hello.
that whether this block should be removed or it should be stitched. So that is sometimes we feel unnecessarily excavation is to be done, or at times we save it. It only, I mean, experience you can say, but I was little handicapped to take decision on certain places at the site. So I was thinking if there was any such technique which can give a fair idea, but that I
Uh,
again seem.
I can refer you to one of my close friend. He is in Norway, and they have done recently some kind of the aerial survey. Using aerial survey, they try to get very good information. So maybe that their technology may help you. So if you are interested, I can give you his email ID to you. I can.
Sure,
He's
sir.
Dr. Rajendra Basin.
Oh, I
So
know him. I know him
you
very
know,
well. He's
so
from NGI. I
NGI,
know him.
yeah,
Yeah, I know him. I've been working in with him, Dr.
yeah.
Mahdi and Dr. Basin.
Okay,
Both are
okay,
good friend of mine,
okay.
and they had been doing this magnetolography, that
Yeah, yeah,
helicopter survey. Yeah,
yeah.
that I am aware, sir.
So I think they will be the best people if they can provide some solution.
Right, sir. Thank you so much.
Thank you. Nice talking to you.
Same here.
Thank you, sir.
Yes, Mr. Baladhara, you want to ask?
Yes, yes. Hello. Good afternoon, madam ji.
Good afternoon.
Hello.
Yes, please.
Sir, I have two questions, sir.
Yeah.
At first, I wanted to thank to all expert and my NVD officer, sir, and thank you to give me opportunity to ask the question, sir. Uh, my first question is that, sir, if the foundation material are highly erodible and potential consequences of failure are great, then what can design we has to adopted, sir, and what design will be justified, sir?
Can you repeat the question?
If the foundation material are highly
High
erodible
erodible.
It is
and the
rock.
potential consequences of failure are great, so what design we could be adopted, sir, and what kind of design will be justified and appropriate, sir?
Erodible means are you talking about the soils or about the rocks?
Erodible rock, sir. I ask about rock.
It is a rock and jointed rock.
Rock and jointed rock, sir. Okay, sir.
Uh, if it is means erodible means it is easily going away.
Erodible means just like as erosion in soil.
It's then highly weathered kind of the material.
Okay, sir. Highly
Then
weather
then
explorers.
yeah, then in my opinion, you have to maybe replace it. You have to do some kind of the dental treatment. You have to replace that
Okay.
particular material which is really not having the strength. Had it been a very means blocky and means these are the blocks which you are saying that they can be taken away by water force, then there can be bolting and stitching kind of the things can be done. But if it is the rock itself is so poor, then in my opinion, then you have to remove this material, either remove it with some dental treatment, or you go deeper.
Hello.
Yes, please.
Hello. Sir, my next question is, sir, second question. What criteria for acceptability of foundation rock surface? What
Foundation
criteria? What criteria for acceptability of foundation rock surface, sir?
means you want to say where you find that the foundation rock is acceptable.
Okay, okay, sir.
That's what your question is.
Okay.
Probably
And
you want
primary hazard.
you
Primary hazard.
probably you
Primary
want to sorry. Yeah, can you complete?
The primary hazards to high embankment dam are cracking within the cores by unequal settlement and the development of sewage channel along the contact of the impervious core with the foundation and abutment rock.
Yeah.
So either of these defects could lead to failure of the dam.
Yes.
Question is how can we protect the dam for cost to damage?
See, if I talk about the rock surface, it has to be a good surface. Good surface means it's at the surface it is going to be weathered, so that weathered material has to be chipped away. It has to be a rough surface, and
Okay.
you can use the test like Schmidt hammer test, which give you a good idea about the property of the surface. So and means it should be free from defects, all those defects. So you have to chip it. You have to come to the fresh rock. And Schmidt hammer is a very good test which can give you the idea.
Okay.
And obviously it has to be rough. It has to be rough, and then it has to be made integrated with whatever foundation material you are putting on it. There has to be very good bonding between the two materials.
Okay. Good bonding with materials. Materials.
Yeah.
Yes. Do you have any other question? Is there any more questions, please?
Thanks, sir.
If the participants still have any questions, they may write to us as well. We will arrange the answer from the speaker and get back to you over the email. Thank you to the speaker and the participants for the interactive and lively session. I would like to convey my special thanks to Professor Mahendra Singh for sparing his valuable time. Thank you for your time.
Thank you very much. I think I encroached upon the time.
Thank to you too, sir.
Thank you. I'll be happy to have questions if there is some question in writing. Thank you very much.
Thank you, sir. We will now take a break for lunch and reassemble at 1500 hours or after the lunch break session. Thank you all.
Thanks a lot.